So early in 2025, a team of material scientists actually published a paper that is just, well, it's completely wild. They detailed this analysis of a group of extremely well-preserved swords that they pulled from a silt deposit over in the British Isles.
Right, and we're talking about artifacts that date precisely to the 5th century. That really chaotic post-Roman landscape.
Exactly. And I mean, normally when you find 5th century weaponry, you're finding this heavily corroded, low carbon iron, like stuff that looks way more like a rusty sponge than an actual weapon of war, right?
Oh, yeah, absolutely. Just brittle, degraded clumps of metal.
But these blades were entirely different. When the researchers took cross-sections of these artifacts and put them under a scanning electron microscope, the elemental mapping basically forced them to recalibrate their
I
instruments.
remember reading about that. They actually thought their machines were broken at first.
Right, because the spectrograph showed these distinct, totally undeniable peaks for trace elements like vanadium and tungsten. And it was all locked within this high-carbon crucible steel matrix.
And the reason this specific finding sent such massive shockwaves through both the historical and the metallurgical communities is that, well, a crystalline steel structure alloyed with refractory metals like vanadium, it absolutely should not exist in 5th century Britain.
Not even a little bit, right?
Not at all. I mean, the capability to achieve that specific mastery of molecular bonding, to actually engineer that exact iron-carbon vanadium matrix that predates the European Industrial Revolution by a full millennium.
1,000 years.
Yeah, exactly. It is a massive, almost impossible chronological anomaly.
Well, welcome to our deep dive, everyone, because today we are taking the data from that 2025 silt discovery, along with historical records of ancient metallurgy, and we are going to completely reevaluate one of the most enduring narratives in human history.
You really are pulling back the curtain today.
We are. We're looking at the legend of King Arthur's Excalibur. And for you listening, we're stripping away the mystical lady of the lake, the wizardry, all the enchantments. By pitting medieval metallurgy against modern material science, we're exploring the incredibly real probability that the most famous magical relic in all of literature was actually just a highly sophisticated high-tech alloy.
And, the premise here fundamentally changes how we view the transmission of human knowledge. I mean, when you look closely at the Arthurian texts through the lens of modern science, you start to realize the authors weren't just like inventing magical properties out of thin air.
They were describing something real.
Exactly. They were attempting to describe a level of high-performance engineering that was just so far beyond their foundational understanding of physics and chemistry.
So the only vocabulary they had left to describe it was basically the vocabulary of magic?
Right. It was divine intervention to them.
So to really get into this, I was reading through the descriptions of standard 5th century warfare in our source material just to establish a baseline. Because, you and I, we tend to assume a level of parity in ancient battles, right? Like swords clashing against swords, everything is equal.
Oh, sure. Like a movie scene.
Exactly. But the gritty reality of the post-Roman iron industry paints a very different picture of what the average defending Briton or, an invading Saxon warrior was actually swinging around out there.
Yeah, they definitely weren't fighting with polished, shimmering steel.
No, they were largely fighting with weapons forged from bog iron. And understanding the severe chemical limitations of bog iron is just entirely necessary if you want to understand why a crucible steel blade would look supernatural.
Precisely. Because to understand the anomaly, you really have to understand the baseline. And bog iron is, well, it's not mined from deep rocky veins like you'd picture in a traditional mine.
Right, where does it come from then?
It is literally harvested from swamps and peat bogs. And the process is actually biological in origin, which is kind of mind-blowing.
Biological, like from living things.
Yeah. There are these certain iron-oxidizing bacteria, like Gallionella, and they live in these oxygen-depleted, really acidic swamp environments.
Okay, so what do the bacteria do?
So they oxidize ferrous iron into ferric iron, and then that precipitates out of the water and forms these lumpy, reddish-brown deposits right at the bottom of the bog.
So the local 5th century populations are essentially just out there raking up clumps of bacterially processed rusty dirt from a swamp.
That's exactly what they're doing. They aren't dealing with a dense, high-yield ore at all. They're taking these impure, highly porous clumps and just throwing them straight into a bloomery.
And the mechanics of a 5th century bloomery furnace, right, they really dictate the physical properties of whatever weapon comes out of it.
Absolutely. A bloomery furnace is basically just a relatively simple clay or stone chimney. You layer your charcoal and your bog iron ore, and then you pump air in using bellows.
Kind of like a massive, super hot campfire in a tube.
Right, but the critical limitation here is thermodynamics. A bloomery operates at roughly maybe 1,200 degrees Celsius.
Which sounds incredibly hot to me.
It is hot. It's hot enough to reduce the iron oxide, meaning the carbon monoxide from the burning charcoal actually strips the oxygen away from the iron. But, and this is the key point, it is not hot enough to actually melt the iron.
Oh, really? What's the melting point?
Pure iron melts at 1,538 degrees Celsius. So the bloomery is about 300 degrees too cold.
Wow, okay. So instead of getting this nice pool of liquid metal that you can cast or easily mix up, you're getting what, just a solid chunk?
Yeah, you get this solid kind of spongy mass sitting at the bottom of the furnace. It's historically called a bloom.
A bloom, got it.
And it's a completely porous mass of pure iron, but it's mixed with a massive amount of liquid silicate slag.
Slag is just all the melted impurities, right? Like the dirt and the clay.
Exactly. So the blacksmith literally has to pull this glowing, hot sponge out of the furnace and physically hammer it over and over, just to squeeze the liquid slag out of the solid iron.
Almost like wringing out a wet towel.
That is the perfect analogy.
Yeah.
But as you know, you can never wring out every single drop of water from a towel.
Right. There's always going to be some dampness left behind.
Right. And that means standard 5th century iron is absolutely riddled with microscopic and sometimes macroscopic slag inclusions.
So there's literally little pockets of glass and dirt permanently trapped inside the sword?
Yes. And furthermore, because the iron never actually reached a liquid state in the furnace, it absorbs very, very little carbon from the charcoal.
And carbon is the essential element that transforms soft iron into actual hardened steel, right?
Exactly. Without carbon, it's just iron. So the end result of this whole bloomery process is a blade with almost zero carbon, heavily contaminated with silicates.
Okay, let's translate that chemistry into combat physics for you listening. Imagine I'm a Saxon warrior, right? I'm standing in a muddy field. I have a sword made from this low-carbon, slag-included bog iron. I swing my sword and I strike the thick wooden rim of an enemy shield with full force. What is physically happening inside the metallic lattice of my sword at the exact moment of impact?
Well, at the atomic level, pure low-carbon iron is structured in this crystalline lattice. But the bonds between the planes of atoms are relatively weak.
Because there's no carbon holding them together.
Exactly. So when your sword hits that solid wooden shield, the kinetic energy of the impact physically forces those atomic planes to slide past one another.
Ouch.
Yeah, and because there is no carbon in the lattice to lock those planes in place, they slide and then they don't slide back.
I think the technical engineering term for that is plastic deformation, right? The energy of the strike permanently alters the geometry of the blade.
That's the one. The blade literally bends and it just stays bent.
That sounds completely useless in a fight.
It's terrible. And it gets worse. Where there are slag inclusions, those little pockets of glassy impurities we talked about, the atomic lattice is already interrupted.
Oh, I see. So it's already got weak points built into it.
Right. Those inclusions become severe stress concentrators. The kinetic energy from the impact pools at those exact points, and it initiates microfractures.
So the blade starts cracking from the inside out.
Exactly. If you bend a piece of slag-rich bog iron too many times, or if you hit it against something harder than itself, those microfractures propagate right along the inclusion lines, and the whole blade just shatters into pieces.
That is wild. I mean, the sources mention these historical accounts from this general technological era where warriors literally had to step back from the front line of a battle, put their weapon on the ground, and use their heavy boot to stomp their sword back into a relatively straight line before they could keep fighting.
Can you imagine the panic? It is a terrifyingly unreliable tool, especially when your life actually depends on it.
It sounds like a nightmare.
It is the stark reality of relying on materials that possess a really low yield strength. The metal fails structurally long before the battle is actually over. You have this weapon that dulls almost instantly upon striking armor, it bends under moderate kinetic load, and it chips wherever an impurity breaches the edge.
Which brings us perfectly into the stark contrast with the Excalibur mythos, because the early poetic texts, they don't just describe a sword that was merely a little bit better.
No, they describe perfection.
Right. They describe the shimmering blade that retained a razor-sharp edge indefinitely, a weapon that could literally cleave through other iron swords without taking a single notch, a blade that flexed under immense pressure but never, ever broke.
And when you view those specific physical attributes against the backdrop of regular warriors stomping their bent swords flat in the mud, Those poetic descriptions sound exactly like a modern high-carbon spring steel.
It's almost like someone dropped modern technology into the 5th century.
It really is. They are describing a material that has completely mastered the fundamental paradox of metallurgy, which is the war between hardness and toughness.
I want to break that down because I think people use those words interchangeably, but in material science, they mean very different things.
Oh, absolutely.
Yeah.
They are generally inversely correlated. So if you want a material to be incredibly hard, meaning it can hold a really sharp edge, you increase the carbon content.
Right, like cast iron.
Yes,
Yeah.
or even glass. But high-carbon materials like that are incredibly brittle. They completely lack toughness.
So if you strike them hard, they don't bend, they just shatter.
Exactly. The atomic lattice is so rigidly locked that it cannot absorb energy elastically.
Conversely, if you want toughness, which is the ability to bend without breaking, you have to remove the carbon.
Right. You get something like soft bog iron or copper. It flexes beautifully, but it can't hold a sharp edge to save your life.
So the anomaly of the 2025 silt blades, and really the hypothetical reality of Excalibur, is that they somehow exhibited both extreme hardness and extreme toughness simultaneously.
Yes. And the only way to achieve that in the ancient world was through the incredibly complex, highly controlled process of creating crucible steel, which is historically known in later centuries as wootz steel.
I really want to dig into the thermodynamics and the chemistry of this crucible process, because it is fundamentally different from that open-air bloomery furnace we just talked about.
It's like night and day.
We established that a bloomery can't actually melt iron. So how on earth does a 5th century smith cross that 1538-degree threshold to actually liquefy the metal and create this high-tech alloy?
Well, it requires an entirely different approach to thermal containment. A crucible is a sealed container made of highly specialized refractory clay.
Refractory clay, what makes that special?
It's clay that is super rich in alumina and silica, which allows it to withstand extreme thermal shock without melting or cracking apart in the fire.
Okay, so they have this super durable clay pot. What goes inside?
The smith places pieces of the raw bloomery iron, some organic material to provide a carbon source like specific leaves, certain woods, or even bone. And crucially, they add a flux material. Then they seal this clay vessel completely shut.
I was looking at the chemical role of the flux in these sealed environments in our source material. A lot of ancient texts mention adding crushed glass or really specific types of sand into the pot.
Yes, that's the flux.
And in a standard bloomery, the slag is just this annoying byproduct you have to hammer out. But in a crucible, the flux is actively manipulating the chemical environment inside the pot.
Oh, it is actively engineering the purity of the steel. The flux, like that crushed glass or calcium-rich material, serves multiple vitally important functions.
Like what?
Well, first, it melts at a much lower temperature than the iron does, so it forms a liquid pool inside the crucible early on. As the iron begins to heat up, this liquid flux acts as a chemical solvent.
A solvent, so it's kind of like soap.
Basically, it binds with the silicate impurities, the sulfur, and the phosphorus that are trapped inside that spongy bloomery iron.
So it's essentially washing the iron at a molecular level.
That is a great way to visualize it. It actively absorbs the impurities right out of the metal. Furthermore, because the liquid flux is lighter than the heavy iron, this liquid slag floats to the very top of the crucible.
Like oil floating on water.
Exactly. And once it's floating on top, it forms this perfect protective liquid seal. Because even though the clay crucible is closed, there is still some oxygen trapped inside the chamber.
And oxygen is bad for steel, right?
Very bad. The liquid slag layer prevents that ambient oxygen from reaching down and reacting with the carbon. If the oxygen did reach the carbon, it would form carbon monoxide gas and just escape, completely ruining the carbonization process.
Wow. So the flux is both a chemical sponge for impurities and an atmospheric shield at the same time.
It really is brilliant. And because the crucible is completely sealed, and the smith is using specialized forced air draft kilns, the internal temperature can finally breach that 1500-degree mark.
So the iron actually liquefies. It turns to soup.
Yes, and this is where the real molecular magic happens. In a liquid state, the iron atoms are no longer rigidly locked in a solid lattice. The carbon atoms released by the burning leaves and bone can easily and uniformly diffuse throughout the entire pool of liquid iron.
This diffusion process is what we call creating an interstitial solid solution. And I mean, I just find the atomic geometry of this totally fascinating.
It's beautiful geometry.
It is. Because an iron atom is relatively large, structurally speaking, but a carbon atom is much, much smaller.
Right.
So as the liquid metal begins to cool down and solidify back into a crystalline lattice, the iron atoms arrange themselves into a specific structure. At high temperatures, it's typically a face-centered cubic structure known as austenite, right?
Correct.
And those tiny little carbon atoms, they physically wedge themselves into the empty spaces, the interstices between the much larger iron atoms.
And that physical wedging is the absolute key to incredible edge retention. Remember those slipping planes of atoms in the soft bog iron we talked about earlier?
Yeah, the ones that cause the plastic deformation and the bending.
Right. Well, when carbon atoms occupy those interstitial spaces, they act like microscopic speed bumps. They distort the iron lattice just enough to create highly localized stress fields.
Oh, that makes sense.
So when kinetic energy is applied to the blade during a strike, the planes of iron atoms try to slide past one another just like before. But this time, they immediately hit those carbon speed bumps and are completely stopped.
The slip planes are locked. The blade completely resists plastic deformation.
Exactly. It holds its rigid shape, and therefore it holds its razor edge.
But the true genius of crucible steel, this Woots structure we're talking about, isn't just absorbing the carbon, right? It's the highly controlled cooling process afterward.
Yes, the cooling is arguably the most difficult part. Because if you cool high-carbon steel too quickly, it forms something called martensite, which is incredibly hard, sure, but it is glass brittle. It would shatter in the first swing.
So how do they avoid that?
The crucible process involves an excruciatingly slow cooling rate. We're talking over several days.
Days. Just to cool down.
Yeah, letting the fire die down very gradually. This incredibly slow cooling allows the carbon to precipitate out of the solid solution and form microscopic, ultra-hard layers of iron carbide, which we call cementite.
Okay, so you have these super hard layers forming.
Right, but they are interspersed within softer, tougher layers of lower carbon iron, called ferrite or pearlite.
Oh, wow. So it's essentially creating a composite material engineered right at the microscopic level.
That's exactly what it is. You have the hard cementite layers acting like a skeletal structure to hold that razor edge, and they're surrounded by the softer ferrite layers acting like shock absorbers to provide flexibility and prevent the cementite from shattering.
That is the precise mechanism that solves the hardness versus toughness paradox. It is a literal masterpiece of materials engineering.
It really is. But to see this level of engineering in post-Roman Britain presents an enormous historical puzzle for us.
Right, because we generally associate this specific Woots crucible mastery with southern India and the Middle East, peaking centuries later in the production of Damascus steel.
Exactly. It shouldn't be in a muddy British swamp in the year 450.
Which forces us to ask you, listening, how on earth did this localized anomaly exist in 5th century Britain? And the sources suggest two primary hypotheses.
Yes, they do.
The first is what we'd call a remnant trade route. The idea that maybe a single Woots ingot, or perhaps even a finished blade, made its way from the east, traveling across the crumbling Roman infrastructure before the trade networks completely collapsed.
I mean, the Roman Empire certainly had expansive trade networks, and there's definite archaeological evidence of trade with India. A high-value item, like an advanced steel ingot, could theoretically have been transported all the way to Britain. But the timeline and the sheer logistical chaos of the 5th century make this highly, highly precarious. By the time the Arthurian legends are set, the Roman legions had officially abandoned Britain. The economy was heavily localized, it was fractured, and long-distance luxury trade had largely evaporated.
And honestly, I have to push back on the trade route theory for another major reason, and that returns us to the 2025 silt discovery.
The elemental profile.
Exactly. If these blades were just imported Indian Woots, their chemical signature should match the ores found in southern India. But the massive presence of vanadium and tungsten in those 2025 samples points toward a very different conclusion.
It really does.
Does the elemental profile align with any known Woots deposits from the east?
That is the pitiable observation right there. No, the elemental profile does not perfectly align with standard Eastern Woots.
Not at all.
Not at all. The specific concentration and the unique combination of those trace elements, the vanadium and the tungsten, strongly suggest a highly localized, distinct ore source right there in the British Isles.
Which brings us to the second and honestly much more compelling hypothesis. An accidental, highly localized smelting breakthrough.
A true micro-event.
Yeah, like a perfect storm where one specific smith, using a highly specific, localized polymetallic ore vein, accidentally engineered an alloy that vastly surpassed anything else on the entire planet at that time.
It's an amazing thought.
Let's look closer at the scanning electron microscopy data from those silt blades, because the presence of vanadium and tungsten isn't just like a chemical fingerprint for tracking down the ore's origin.
No, those elements actively change the physics of the steel itself.
They do, and their presence elevates the blade from just being high-quality steel to an absolute metallurgical anomaly.
Under the electron microscope, the researchers were able to deeply analyze the grain structure of the steel. You see, as liquid steel cools and solidifies, it doesn't just form one single, massive, continuous crystal.
Right, we talked about that.
It forms millions of microscopic crystals, which we call grains, and they grow outwards until they bump into one another.
And the borders where all these tiny crystals meet are called grain boundaries.
Precisely. And the size of those individual grains directly dictates the overall mechanical strength of the sword. There is a fundamental principle in material science known as the Hall-Petch effect.
Okay, what does the Hall-Petch effect tell us?
It essentially states that the smaller the grains are within a crystalline metal, the stronger and the tougher the overall metal becomes.
Because there are more boundaries.
Yes. When a crack begins to propagate through a piece of metal, say, from the heavy impact of blocking an incoming axe, that crack travels very easily straight through the orderly atomic lattice of a single large grain.
It just unzips it.
Right. But when that crack reaches a grain boundary, the disorganized, messy atomic structure at that boundary acts as a massive roadblock.
Oh, I see.
The crack has to expend a huge amount of its kinetic energy just to change direction and push its way into the next grain. Therefore, if you have much smaller grains, you inherently have exponentially more grain boundaries.
More roadblocks.
Exactly.
Yeah.
Millions more roadblocks. So the material requires vastly more kinetic energy to actually fracture.
Okay, so how do our trace elements fit into this microscopic picture? What are the vanadium and the tungsten actually doing inside that crucible during the slow cooling process to physically shrink the grain size?
Well, vanadium and tungsten are what we call refractory metals. And chemically, they act as incredibly powerful grain
They're
refiners.
grain refiners. Okay.
When they are present in the liquid steel, even just in fractions of a single percent, they actively bond with the available carbon to form microscopic, unbelievably hard particles called carbides, specifically vanadium carbides and tungsten carbides.
So these little carbides are forming while everything is still liquid.
As it's just starting to transition, as the steel begins to cool and turn from liquid to solid, these tiny, incredibly hard carbides act as nucleation sites.
They act like seeds.
That is the perfect word for it. They are seeds. The iron crystals begin to form and grow around these millions of dispersed carbide seeds simultaneously.
Because there are so many of these little seeds scattered uniformly throughout the cooling liquid, right?
Exactly. And because there are so many of them growing at the exact same time, the iron grains bump into each other very quickly. They simply don't have the physical space or the time to grow large.
That is so elegant. But there is also a secondary mechanism happening here, right? Something called Zener pinning. I was looking into how grain boundaries move at high temperatures, and it seems relevant here.
Oh yes, Zener pinning is absolutely crucial to the anomaly. You see, even after the metal has fully solidified, if it remains at high temperatures, which remember it does inside that slow cooling crucible for days, the grains can actually continue to grow
Wait, how do they grow if they're already solid?
by slowly absorbing the smaller neighboring grains. It's a thermal process called grain growth. But those microscopic vanadium and tungsten carbides that we just talked about, they end up sitting physically right on the grain boundaries.
Oh, wow.
Yeah, they act like chemical anchors, or almost like microscopic rebar. They pin the boundaries in place, physically preventing the grains from expanding and absorbing each other.
So by sheer dumb luck, this 5th century smith used a batch of ore that naturally contained the precise trace elements necessary to force the steel into an ultra-fine, tightly packed microstructure.
Exactly. They didn't understand the chemistry of nucleation.
Yeah.
They'd never heard of Zener pinning.
They didn't even know what a trace element was.
No, not at all. But the result of their fire was a blade with a grain structure so impossibly refined that it could absorb kinetic impacts that would instantly shatter any standard Saxon weapon.
The smith just knew that the ore from, say, one particular rocky outcrop over the hill, when processed in their specific clay crucible, produced a metal that behaved like absolutely nothing else on Earth.
It is the absolute definition of accidental genius.
But, I do want to challenge the source of those trace elements for a second, because our sources mention a biological alternative. Could the vanadium have actually come from the organic material used inside the crucible rather than the iron ore itself?
That's a really interesting angle.
Because certain plants are known hyperaccumulators, right? They actively draw heavy metals out of the soil and store them in their leaves and stems. So if the smith used a really specific type of plant matter for their carbon source, could that be the real source of the anomaly?
It is a totally valid scientific question. Phytomining, which is the accumulation of metals by plants, is a well-documented phenomenon. However, the concentration levels of vanadium and tungsten required to significantly alter the grain structure of a multi-pound solid steel ingot via carbide formation. While those levels generally far exceed what could be deposited purely through the ash of some organic material in a tiny crucible.
It just wouldn't be enough volume.
Right. While tiny trace amounts might be introduced biologically, the specific, really robust elemental peaks seen in the 2025 EDS analysis strongly indicate that the base iron ore itself was mined directly from a highly localized polymetallic vein.
Okay, so we're essentially looking at a geological lottery combined with a metallurgical accident.
A 1 in a million shot.
And because it was so hyper-localized, it perfectly explains why this technology didn't spread across Europe. It explains the total impossibility of mass production.
Absolutely.
I mean, if you are the local king who commands that one specific mastersmith, and you control that one specific rocky hill containing the polymetallic ore, you can forge a handful of these Excaliburs.
You can outfit yourself and perhaps, a few of your most elite champions.
Your Knights of the Round Table, so to speak.
Precisely. But you cannot outfit an entire army. You cannot industrialize a process when you don't even understand the underlying chemistry making it work.
Yeah, right. If that single vein of ore runs dry, or if the smith suddenly dies without passing on the highly intuitive, unwritten knowledge of the exact kiln temperatures, the technology simply vanishes.
Poof, gone.
And that rarity is the absolute key to the mythology. If there are only, let's say, 5 of these unbelievable swords in existence in the entire British Isles, and they are wielded by a highly successful warlord, the narrative naturally shifts, doesn't it?
It has to. It shifts from, this is advanced localized metallurgy to, this is literal divine intervention.
Which allows us to re-examine the core Arthurian legends not as pure fantasy, but as misunderstood technical manuals and observational physics.
I love this part.
It's my favorite. Let's look at the foundational myth. The sword and the stone. A young Arthur pulls a sword from a solid rock, an act that proves his divine right to rule, because literally no one else possessed the strength to move the blade.
It's the classic hero's journey starting point.
But if we discard the magic entirely, how does materials science explain a perfectly forged sword embedded inside a solid rock?
Well, we have to return to the physical reality of the crucible steel process we were just discussing. We established that the iron, the carbon, and the flux are all sealed inside a clay crucible and heated until completely liquid.
Right, the 1500-degree suit.
Yes, and as the metal cools incredibly slowly over several days, the heavy, dense Wootz steel ingot, which metallurgists often call a button, solidifies at the very bottom of the crucible.
Because it's the heaviest material.
Exactly. But what happens to the flux and all those absorbed impurities that were floating on the top?
Well, as the temperature drops, that liquid slag layer also has to solidify.
It does. And because it is composed largely of silicates, calcium, and glass, it cools into this extremely thick, rock-hard, glassy crust, sitting directly on top of and fully encasing the top half of the steel button.
So, to a layman observing this process, once the clay crucible is cracked open and broken away, the steel ingot appears to be firmly embedded right inside a solid piece of dark, jagged stone.
It looks exactly like a sword and a stone.
But the stone isn't geology at all. It's industrial waste. The stone is just the slag.
Exactly. And extracting that precious steel button out from the glassy slag matrix is not just a simple matter of hitting it really hard with a hammer.
Why not? I mean, if the steel is so strong, why can't you just smash the brittle slag right off of it?
Because of the differing thermal expansion coefficients and the residual stresses inside the materials.
That sounds dangerous.
It is. As the slag and the steel cool inside the crucible, they contract at very different rates. This creates immense mechanical tension right at the boundary where the two materials meet.
So they're basically fighting each other as they cool down.
Yes. Furthermore, before the Wootz ingot is properly forged and heat-treated in a forge, the raw button still contains heavy, unbroken networks of that brittle cementite we mentioned.
Oh, so it's vulnerable at this stage.
Highly vulnerable. If you strike the glassy slag too hard, or even just at the wrong angle, the kinetic shock wave transfers directly into the untreated steel. It can easily propagate microfractures, completely shattering the priceless ingot before it is ever even forged into a blade.
Oh, wow. So the smith literally has to understand the cleavage planes of the silicate rock.
They do. They have to know exactly where to strike the stone and with exactly the right amount of force to fracture the slag safely without transferring that destructive energy into the steel core.
It requires an incredible intuitive mastery of the material. A lesser smith or, an untrained apprentice would swing a heavy hammer, fail to break the slag efficiently, or much worse, just ruin the steel entirely.
Only the master smith, the chosen one, if you will, who truly understood the exact mechanics of the material, could successfully strike the matrix and extract the pure steel from the stone.
That completely recontextualizes the myth for me. The entire legend of the chosen king pulling the sword from the stone is essentially just a multi-generational game of telephone.
Its oral history degrading over time.
It began as a perfectly accurate description of a highly specialized metallurgical extraction process. And then generations later, after the localized knowledge of crucible steel had been completely lost, oral storytellers who had absolutely no concept of smelting or slag, they translated the story into a literal magical boulder and a boy ordained by God.
It is a profound example of how humanity preserves complex technical knowledge through allegory, specifically when the actual scientific vocabulary is lost.
And we see this exact same translation of science into magic when we look at the battle physics of Excalibur.
Oh, the combat accounts are fascinating.
They really are. Why did the blade seem to possess an invincible magical aura when it actually struck other weapons on the battlefield? We established earlier that standard Saxon weapons were highly prone to plastic deformation. They bent, they chipped, they broke.
They failed constantly.
But the accounts of Excalibur describe a weapon that not only didn't break, but seemed to effortlessly shatter the weapons of its opponents, all without even jarring the arm of the wielder.
How did the trace elements and that woot structure actually achieve that specific kinetic result?
Well, it fundamentally comes down to acoustic impedance and harmonic resonance during the transfer of kinetic energy.
Acoustic impedance, like sound waves.
Yes. When two swords clash at high speed, a massive amount of kinetic energy is instantaneously introduced into both blades. This energy propagates through the solid metal as a stress wave, which is essentially an acoustic wave.
Right, the blade physically vibrates, ringing like a bell.
Exactly. But how the metal internalizes and handles that violent vibration dictates what happens next. In the soft, low-carbon bog iron, the atomic lattice is relatively loose, right? And it's filled with those microscopic slag inclusions.
So it has really poor elasticity, parable elasticity. When the shock wave hits, the lattice cannot efficiently transfer the energy along the length of the blade. The energy gets stuck. It pools at the exact point of impact and at those microscopic defects, rapidly exceeding the metal's yield strength.
And that's when the metal rapidly undergoes plastic deformation. It bends deeply or literally tears apart.
It absorbs the destructive force by physically yielding to it. It sacrifices itself.
Conversely, the high-carbon crucible steel blade, which is tightly reinforced by those vanadium and tungsten carbides, possesses an incredibly tight, highly elastic atomic lattice.
It behaves just like a very stiff modern spring. When the impact occurs, the lattice compresses elastically, then immediately snaps back. It transfers the shockwave efficiently through the entire length of the blade, where it is harmlessly dissipated into the air as sound and heat.
I want to use a mechanical analogy here for our listeners to really visualize the impedance mismatch between these two competing weapons.
Go for it.
Imagine taking a solid, extremely dense oak baseball bat and swinging it as hard as you possibly can against a hollow, thin-walled PVC pipe.
That's a great visual.
The oak bat is dense and rigid. It transfers the impact energy efficiently. But the PVC pipe simply cannot absorb or reflect that much kinetic energy elastically.
Right, it doesn't have the structure for it.
The result is that the PVC pipe shatters violently into pieces, while the oak bat barely even vibrates in your hands.
And that acoustic impedance mismatch dictates that the weaker structure always absorbs the catastrophic failure.
So in the context of a dirty 5th century battlefield, when Excalibur strikes a standard bog iron sword, the high-tech Wootz alloy acts exactly like that oak bat.
It completely resists deformation and efficiently transfers almost all of the kinetic energy directly back into the opposing weapon.
And the bog iron weapon, unable to cope with that sudden, massive influx of energy, just shatters.
And crucially, because the crucible steel blade transfers its energy so incredibly efficiently, the wielder Arthur, in the legends, feels almost no jarring shock in their own arm.
That must have felt like a superpower. They swing, The enemy's sword literally explodes into tiny pieces, and their own blade remains completely pristine, just humming lightly in their hand.
To a 5th century warrior observing this happen, it completely defies the observable laws of nature. I mean, they know that when iron hits iron, both pieces should notch or bend or ring violently.
It's common sense for them.
Exactly. So when one singular blade violates that basic physical reality, the human mind immediately attributes it to enchantment. The actual physics of vibration dampening and elastic limits are translated directly into the magic of an unbreakable, invincible weapon.
Which brings us to what I think is the ultimate tragedy of this whole technological anomaly.
Loss of the knowledge.
Yes. We have identified a localized metallurgical process that was capable of producing a blade with a highly refined grain structure, superior edge retention via cementite networks, and incredible elastic toughness.
It was a technological leap that absolutely should have revolutionized European engineering.
But it didn't. It vanished entirely, leaving the era to be cemented in history as the Dark Ages. If this technology was really so vastly superior, a literal cheat code for ancient warfare, why did it disappear so completely?
Because specialized high-performance technology is intrinsically fragile, particularly when it relies on non-standardized infrastructure.
Right.
To really understand the disappearance of Excalibur's underlying technology, we have to look at the socio-political collapse of the era. The production of crucible steel was not a resilient, redundant industry like we have today.
It was a highly delicate micro-industry, totally dependent on extreme specialization.
Exactly. You can't just build a 1,500-degree kiln anywhere you want. You mentioned earlier that the crucible requires highly specific refractory clay.
Right, the clay with the high alumina and silica content.
Those aluminosilicate clays, once capable of withstanding those temperatures without melting, they're not just found in every random riverbed. They are geologically very specific.
So, if a master smith has established a successful kiln site near a specific clay deposit and a specific polymetallic ore vein containing the vanadium,
Their entire production capability is completely geographically locked to those specific coordinates.
and post-Roman Britain in the 5th and 6th centuries was practically defined by geographical instability.
Absolutely. The infrastructure of the Roman micro-empire was totally collapsing under the weight of sustained Saxon invasions, shifting local borders, and severe agricultural famine.
The supply chains literally disintegrated.
If a rival warring faction takes over the valley containing your refractory clay, well, you can no longer build the crucibles. If that single localized vein of trace element-rich ore is exhausted, or it's lost to enemy territory, you can no longer engineer the grain refinement.
But the most fragile component in this entire chain isn't the clay or the ore, is it? It's the knowledge itself.
Without question. The complex knowledge required to execute this process was not written down in standardized chemical formulas in a textbook. It was entirely experiential and intuitive.
Passed down by word of mouth.
And by sight. The master smith just knew the exact shade of yellow-white the fire needed to reach. They knew exactly how the molten flux should smell, or how it should sound bubbling when it was finally time to let the crucible cool.
They knew exactly where to strike the slagstone just by looking at the microscopic spiderweb fractures on its surface.
That level of deep intuitive mastery takes an entire lifetime of trial and error to develop. And in an era defined by violent raids, warfare, and plagues, lifetimes are routinely cut very short.
If the master smith dies before a decade-long apprenticeship is fully completed,
Then the nuanced, unwritten knowledge of the specific thermal cycles and the exact ore identification dies right along with them.
the kilns crumble into the dirt. The specific ore veins are overgrown and forgotten. The remaining Wootz blades are slowly lost to battle or rust, or they're buried deep in the ground as grave goods.
Within a single generation, the physical capability to manufacture high-carbon crucible steel in Britain simply ceases to exist.
It is a stark, almost scary reminder of the sheer fragility of human progress. You know, we often default to this comforting idea of history as a steady, inevitable march forward.
That progress is permanent.
Right. That once a technological peak is reached, it is permanently secured for everyone. But here we have the absolute summit of ancient material science, this brilliant anomaly of molecular bonding.
And because it couldn't be scaled up and was confined to the intuitive minds of a few isolated masters, it just slipped right through our fingers.
The physical reality of the engineering dissolved, and only the awe remained. The science retreated back into the earth, and the cultural memory of those invincible blades was gradually woven into the oral traditions, evolving into the fairy tales and the magical myths we recognize today.
The final verdict of the 2025 scanning electron microscopy data is that Excalibur really must be remembered not as a divine relic, but as a fleeting, gorgeous masterpiece of experimental high-performance engineering.
As we wrap up this deep dive, let's just take a moment to survey the immense ground we've covered today. We started by defining the gritty baseline reality of 5th century warfare, really examining the severe chemical limitations and the plastic deformation of bacterially harvested low-carbon bog iron.
And we contrasted that fragile, muddy reality with the demanding, high-heat thermodynamics of the sealed crucible process.
We analyze how a molten flux layer actively protects the carbon diffusion process, allowing the creation of that critical interstitial solid solution.
Then we explored the groundbreaking 2025 silt data, focusing specifically on how trace refractory metals like vanadium and tungsten act as critical grain refiners.
Utilizing carbide nucleation and Zener pinning to physically force the steel into an ultrafine, highly resilient microstructure.
And finally, we translated the beautiful poetry of the myths directly into the hard physics of material science.
We revealed the sword and the stone to be a very literal description of extracting a Wootz ingot from a cooling matrix of glassy silicate slag.
We explained the magical invincibility of the blade in combat through the mechanics of acoustic impedance and harmonic energy transfer.
And finally, we acknowledged the tragic fragility of the specialized infrastructure that allowed the technology to vanish completely into the Dark Ages.
It is a comprehensive scientific reconstruction of a lost technological peak. It beautifully bridges the gap between medieval metallurgy and modern analytical chemistry.
Which leaves us with a profound question about the nature of the stories we tell ourselves. We've just spent the last hour using scanning electron microscopes and energy dispersive X-ray spectroscopy to prove that the magical Lady of the Lake and the sword and the stone were simply humanity's desperate attempt to describe advanced high-carbon steel and cooling slag using the absolute only vocabulary they possessed at the time.
We have successfully decoded the magic into metallurgy.
If that is true for King Arthur, take a long look at the other fantastical myths etched into our history books. Look at the chariots of fire, the unbreakable shields of the gods, the massive city walls that supposedly fell to nothing but the sound of trumpets. Which of our other ancient fairy tales are actually just highly accurate descriptions of misunderstood, lost technologies, quietly waiting in the dirt for a modern microscope to finally decode them?